Hello everyone. So I welcome you once again in my lecture. Today we are going to talk about heap. Heap is one of the important data structures which is used to implement many of the applications. We will see that many of the operations are very efficient when we apply the heap data structures. Also, the heap data structures is used to uh, sort the sequence of data. We call it heap sort. So first we understand what is heap, and then we will see that how the concept of heap can be used to apply for sorting. That is heap sort. Okay, so let's start. Before we actually discuss what the heap is, let us have a look on certain operations. So now here you can see that we have different kind of data structures we are using, and we want to perform certain operations. Let's say insert, search, finding the minimum, and the deleting the minimum element. So if we have an unsorted array with us, and if you want to perform the insert operation, it will take big O of one operation because the array provides us random access. So if you want to insert any element, you can insert it in big O of one time. That it will take constant time. You have to go to that index and insert it. If you want to search any element, then because we have this is unsorted array, we cannot apply binary search, so the running cost will be big O of n. To find the minimum element, again you have to apply the linear search. This is will be take big O of n time. If you want to delete this element, then again big O of n time. Now in place of unsorted array, if we have a sorted array, in that case, what is the performance of these operations? Let us have a look. So for insert operation, it becomes big O of n, because if you want to insert a value in between, then you have to make the shifting of all the elements which comes after the required position. So it will take big O of n. Search operation will be log of n, because if the array is sorted, we can go for the binary search, and binary search is log of n. If you want to find the minimum, then obviously if it is sorted, then you can get the first element. If it is ascending order, then the first element will be the minimum element, and the cost is constant big O of 1. But in case of deletion, if the array is sorted and if you want to delete the element, though the element exists at the first position, but again because you are maintaining the array as a sorted array, you need to shift all the element one position, so it will take big O of n time. Now in place of array, we are using linked list to perform this operation. So for insertion, it will take big O of 1. For searching any element, you need to do n operations, then big O of n. Finding the minimum will also be big O of n. Similarly, if you want to delete the minimum, then big O of n. Now let us look to the heap. So if we are using heap in place of all these three, then what is the performance? If you insert any element in the heap structure, then it will take log n time. If you want to search any element in the heap structure, it will take log n time. If you want to find the minimum, then it will take constant time if we are talking about the minimum heap. So heap will be of two forms, max and min. So if you want to find the minimum in the minimum heap, it is constant operation. If you want to delete it, again it's a constant operation. So what is the observation? The observation is, if you are making an application where the operations will be of this kind, if you want to do insertion, searching, finding the minimum, or finding the maximum, or deleting the maximum or minimum, in that case you will observe that most of the operations will be either constant or log n time. But in the other cases, you can see most of them will take order of n time. So we can we can realize that if the application is to be performing this kind of operation, then heap will be the best choice for implementation of data structure. So in that case, the heap will be the best data structure to make our application efficient. So now let us see in detail what is heap. So heap is basically a binary tree which has some special properties. Now what is binary tree? Binary tree is a tree where each node can have maximum two child. Each node has maximum two child. That means a node can have no child, it can have one child or two child. So it's a special binary tree which also conforms to two other properties, that is the heap structure and the partial order property. So if binary tree fulfills these two properties, then that binary is said to be a heap. Now what is a heap structure? Heap structure says a binary tree is said to be a heap structure if and only if it satisfies the following condition, that is regarding the height of the tree. Now what is that? It says the tree T is complete at least through depth h minus 1. So heap structure means the binary tree must be fulfilling the complete tree property. It means that all the leaves must be existing at the depth h or at the depth h minus 1, means at the last level all the leaves must exist or at the second last level, and all the nodes must be inserted from left to right. Then the second property is partial order property. The partial order property is the node must be either maximum from its child, or the key value at the node must be minimum from its child. What does that mean? Partial order property means if we have to make a tree in such a way which contains some key values, let's say 12, then these values left and right child must be less than 12. So this is a scenario for max. And when I say min, in the case of min, the parent node must be minimum among its child. It will be minimum among its child. What does that mean? It means if this value is 2, this value is 7, then if this value is 1, then it is okay. So in the minimum, in the mini heap, the parent node must be less than or equal to its child, and max heap, the parent node must be more than or equal to its child. So if the binary tree is fulfilling these two properties, then it is said to be a heap. Let us see the different type of binary trees to understand in a better way that what exactly the heap is. So the first thing is full binary tree. So full binary tree, here every node other than the leaf has two children. So if you look at this tree, every node other than the leaf is having a two children, or you can say every internal node must be complete, or every internal node must have two child. So I can write here internal node must have two child, then it is said to be a full binary tree. Complete binary tree, as I already said, that complete binary tree is a tree in which the nodes are inserted from left to right, and the leaves can exist at the last level or at the second last level. So here you can see that the nodes are inserted from left to right, 0, 1, 2, 3, 4, 5, and all the leaves are existing at the last level. So perfect binary tree is a tree which is actually complete and also full, and all its leaves are existing at the last level. So let us see that what kind of trees are these which are represented here. So if you look at this, now this is said to be neither complete nor full. Why this is neither complete? Because if you want to have a complete tree, then the nodes must be inserted from left to right. What does it mean? It means when you are inserting this node, then this node, then this node, then you make this insert this node, then this node, then this, then this, then when you move here, then if you want to insert a new node, it should be coming here. It should not go at this position. So this is not fulfilling the complete tree. And also, what about the full property? So full property said that every internal node must have two child. Now if you look at this, this is an internal node, but it does not having a two child, so this is neither complete nor full. Now look at this. This is complete but not full, because it fulfills the property required for the complete. But why not is it Why it is not full? Because every internal node is not having two child, so this is complete, but this is not full. If you look at this, this is full but not complete because every internal node is having the two child, but the nodes are not inserted with the property that the node must be inserted from left to right. That means before filling this left child, we need to add the node to this particular node, then only it's said to be a complete. So again, this is actually full, but it is not fulfilling the condition of complete tree. Now if you look at this, it fulfills both the conditions. It is inserted from left to right. All the leaves are existing either at the last label and the second last label, and all the internal nodes are having the two childs. So this tree is said to be a complete and full. Now we'll see these trees and we'll find out that these are heaps or not. So this is a two tree. So two trees is actually a proper binary tree where every internal node is actually having the two childs, but this is not a heap because it does not fulfill the complete property. So if any binary tree fulfills the structure property, that means if it is complete, and the order property, that means the relationship between the key values, if the two things are maintained, then only it is said to be a heap. So because we don't have a key values here, so we cannot talk about this property, and this is not a heap. Similarly, we don't have any key values here and we cannot talk about the order property, so this is not a heap. Now we have the key values here, so we can look for this property to satisfied or not. So if you look here, that this is actually complete, yes, this is complete. And also if you look that every node is actually more than its child, so this node is more than its child value, every node is more than a child value. So when I say heap, then this property must be satisfied at each label, at each node. So this is a heap, and when you find that the parent node is having a value more than the child, then it is said to be a max heap. So this is a max heap. Now if you look at this, this tree is also fulfilling the complete property, that is called structure property is being satisfied here because this is a complete tree. And also if you look, all the nodes key values are satisfying the relationship of order property, that is the parent value must be more than or equals to the key value, must be equal to the child values. So you can see that every node is actually more than its child key values. So this is also a heap, and this is a max heap because the parent is keeping the maximum value than its child. We have certain properties of binary tree which is also applicable for analyzing the heap. So let us look at these properties. Now the height of the binary tree is log n. This is very important properties. Now these are the properties that we have to keep in mind because these properties will be used when we analyze the performance of the heap operations. Then we have second property, maximum number of nodes in a complete binary tree of height h is 2h plus 1 minus 1. So how to define height? So let us consider one tree. This is one tree, and height is the maximum number of edges from root to leaf. So you need to look from the root to the leaf the maximum number of edges, that will give you the height of that tree. So if you look at this, this is a root, so we can find 1 2 1 2 1 2. So here the height is 2. So if you want to find out that with the height 2 how many maximum number of nodes are possible, that we can find out with this formula. So for this kind of tree with height 2, how many maximum nodes are possible? So we can write 2 2 plus 1 minus 1, which is 7. So with any binary tree with height 2 can have maximum 7 nodes. So you can see here 1, 2, 3, 4, 5, 6, and 7. So this is a maximum possibility. Similarly, if you want to find out that how many nodes of a binary tree with height 3, then you can see this is be 2 power 3 plus 1 minus 1, that is 15. So if you just make one more label here, you will find that the maximum possible nodes will be 15. So at any point of time, if you want to find out the maximum number of nodes, we can use this formula. All leaves in the tree are consecutive and starts at floor n by 2 plus 1 to n. Now when you make a heap, because it's a complete tree, so all the leaves are actually consecutive, and you can find the leaves starting position is floor n by 2 plus 1 to n. What does that mean? If I make a tree something like this, now in this case how many nodes are there? 1, 2, 3, 4, 5, 6. So 6 by 2, 6 by 2, and we take the floor value of this. So 6 by 2 is actually 3 plus 1. So 3 plus 1 is 4. That means from 4 to the last node. Last node here is 6. So from 4 to 6 all are leaves. So this is 1, 2, 3, 4, 5, 6. So you can see here that from the 4 onwards this is a leaf, leaf and leaf. And this property is applicable for all heap. All the leaves will be consecutive and will start from n by 2 plus 1 position to the last position. Every node in heap is heap in itself. So when we say a heap, then we are not looking only at the root node, but every node of that heap must fulfill this property. What property? The order property and the structure property. So entire tree must be fulfilling at every node these two properties, then only it is said to be a heap. Binary heap can be implemented in array using relationship. Now heap is basically implemented by a binary tree, by a ternary tree, or by a n-array tree. The most fundamental implementation is using a binary tree. So binary heap is basically implemented using a binary tree where every node can have maximum 2 child. So how we can use the array for implementing a binary heap? Let's see this formula. So here we can see that left child can be find out by 2 into index, right child can be find out by 2 into index plus 1, and parent will be find out by index by 2. Okay, let's understand in a better way that how we can use an array to represent our binary heap. So let's say this is our tree with the key value a, b, c, d, e and f, and its index is 1, 2, 3, 4, 5, 6. So let's say this is your a, b, c, d, e, f. This is your first position. 2, 3, 4, 5, 6. So if you want to find out the right child of this b, now right child of b means this is at index 2. So right child you can find out by 2 into index plus 1. So 2 into 2 plus 1, that is 5. So at index 5 you will find e. So the right child of b is e, and you can see it is here. So we can simply use an array using this relationship, and we can find out the left child, right child and parent of any node. Now one thing to note here is that when we use a programming language, then this first index is not 1 but it is 0. So we need to make some changes here. So we can represent our array as a, b, c, d, e, f, and here the index is actually 1, 2, 3, 4, 5. So that means when we make a tree, then in that case we will not start our index from 1 but we start from 0. So that means 0, 1, 2, 3, 4, 5. In that case, if we want to implement this program using a programming language, then we have to make a slight change here. In that case, what we will do, we will represent our left child with the formula 2i plus 1, and the right child with 2i plus 2, and the parent will be find out by finding the ceil of I by 2 minus 1. So let's see that how it works. So let's say I am interested to find the left child of C. Left child of C. So C is having the index 2. So left child will find out by using this formula. So 2 into 2 plus 1, that is 5. So I go to fifth index, that is F. So we will see that the left child of C is F or not. So if you go here, the left child of C is F. This is correct. Now if I want to find out the parent of E, so the parent of E you can find out by using this formula. So you can write here the index of E is 4, 4 by 2 ceil minus 1. So what you get? This is index 1. So you go to index 1, which is B. So the parent of E is B. So the parent of E is B. So we can use this formula to represent our binary heap using an array. Now we will see that how we can build the maximum heap, or you can say how to construct a heap. Now when I say heap, heap may be of two form. It may be either a minimum heap or max heap. So here first we will see that how to construct a maximum heap. The logic is almost the same in the minimum heap, only a slight condition will check. Here we are using maximum heap. So for that we are using one operation called max heapify. But if you are interested to build a minimum heap, then we will call min heapify, which is just an opposite operation of max heapify. So we'll see one by one that how the things will work. So if you look at this algorithm, it's very easy algorithm, and in the max heapify you need to pass an array. So what we are actually looking for, we have a given sequence, 4 2 9 8 6. Now if I construct a binary tree in this order, let's say 4 2 9 8 6, then this is not a heap because it will not satisfy the the order property says that the parent key value must be more than the child values, so it is not satisfying. So we have giving a sequence and we want to convert this into a build max heap. We want to convert into a maximum heap. Okay, build max heap is a name given to the algorithm, but our objective is to uh, generate or to create a maximum heap. We need to pass an array. So whatever the array you are having, you need to just pass an array, and after doing some processing you will get a sequence which will convert into the maximum heap. So let's see how it will work. Now one thing to understand that the ascending and descending order will always be a heap. So if you are giving a descending order will always be giving you a maximum heap. So descending order will always be a max heap, and ascending order will always be a min heap. So what does that mean? It means if I am giving a sequence, let's say 42 19 13 7 6 1. Now this is a descending order, and if I construct a tree out of that, then what you will find, if I construct a binary tree out of that, 13 7 6 and 1. Now this binary tree is actually fulfilling both the property. It is fulfilling the complete tree property, and it's also fulfilling the order property. So you can see that the key value at any node is actually more than the key value at a child node. So it's satisfied at this point, it's satisfied at this node, satisfied here. So what we observe is, if any descending order is given to you, you can directly get a maximum heap. Similarly, if you have ascending order, it will be giving you a minimum heap. What does it mean? If I am having a sequence like 5 9 17 23 68, in that case if I make a tree 3 9 17 23 and 68, so here you can see that this is a min heap, because here every parent node is having a minimum value than its child. Now that means if I want to construct a heap, I can simply sort the given sequence and I will get my heap constructed. For example, this sequence is given to me. I will apply any sorting algorithm, and with the sorting algorithm I can convert my sequence into a max heap. Okay, this is one way of doing it, but we are not using that approach, but we are doing a different approach. The reason being is, if you apply any sorting technique, the sorting technique, so far we know the best one is n log n. Now n log n, if you apply the merge sort or the quick sort, you are able to uh, convert your sequence into a sorted sequence, so it will be n log n. But if you apply this approach, then we are able to convert our sequence into the maximum heap with order of n. So big O of n is actually better than n log n. So instead of using this approach, we will be going with this approach. So let's see that how this algorithm work. Here first we have to find out what is the size of the array. So we will pass one array into this procedure. This is our max heap procedure that converts the given sequence into a max heap. So first we will find the length of this array, the number of elements we are having in our sequence. Then we will make one loop for I equals to floor a length to down to 1. Now we have already discussed that in the heap the leaf starts from n by 2 plus 1. From this value to the last value all are leaves, and before this value are all internal nodes. So actually when I say this value, that means I want to perform some operation on internal nodes. Okay, so what does it mean? It means if I have this tree, so here this is leaf, this is leaf, this is leaf. I want to perform operation on these nodes. These are internal nodes which are non-leaves. So we have to apply certain operation from the last non-leaf node to the root node. So we'll start from this node, we will do some operation on this node, then this node, then this node, because we are going from a length by 2 from the last non-leaf, because after this onwards we have all leaves. So from this leaves down to 1 means we keep on moving in this way. And what we are doing? We are doing max cpfy. So there is one operation, that is a max cpfy, that will ensure that it will fulfill the order property. So when we apply the max cpfy, it will check that the node maintains that property or not. What property? That the value kept at this node must be more than the value at this node and this node. This is taken care by the max cpfy. So we will be calling max cpfy here, and then we call max cpfy here, and then we call max cpfy here. So how the max cpfy work, that we have to check. So you can say the main procedure that we are doing in the build max heap is implementing the max cpfy procedure. So let's see what is max cpfy.